Okay, great. So Leo, I will turn it over to you.
Hey everyone, my name's Leo, and I'm going to present on my and my fellow peers at UC Davis work on gem5 CXL, which is a full system multi-host simulation infrastructure. So thank you. Okay. So to start off, let's recap a little bit on the current data center challenges that we have. So modern data centers face three major problems of total cost of ownership. These are sources from Rambus, Microsoft, and Meta that have told us this, and also Google, not shown here, but has also said some of this, which is firstly that there's currently a latency and a capacity gap with traditional monolithic servers. So you have your cache or DRAM, which are fairly fast and fairly small, and then you have your SSD and your hard drives, which are very slow, but very big. There's also a core count difference in the amount of core counts has scaled much higher than the memory bandwidth. So as core counts grow much higher, the memory bandwidth has stayed pretty much stagnant the same. So this kind of limits how much cores can take out of the memory, and essentially subverts the actual usefulness of multiple cores. And of course, lastly, there's a growing amount of stranded memory in data centers due to people either needing more compute than a monolithic server can provide, or more memory than a monolithic server can provide. So the source from Microsoft, for example, says that half of their VMs have 50% of unused memory. And then this, combined with the fact that memory is becoming more and more part of the total cost of ownership of data centers, means that losing out on this precious resource is more and more expensive. Cool. So why Compute Express Link? So first off, let's start with what is Compute Express. So CXL is an open standard for high-speed, low-latency, cache-coherent and interconnect technology for processors, accelerators, and memory expansion devices. So here's an example of like a CXL disaggregated system. You have multiple systems with some accelerators, some smart NICs, all connected to this CXL coherent interconnect. And on the other side, you have memory expansion devices that can all be used by these systems. So this also helps in the sense that this is supposed to be a coherent interconnect. So any system can address another system's memory coherently. So the GPU can access x86 or the x86 system's memory directly. This can also be used to sort of close that stranding problem, since now it can use this memory expansion that is available to all systems. So you don't have to, allocate a whole new system just to use some more compute or more memory, for example. Cool. So CXL has a lot of support. Here is like a show of the board of directors. There's currently a total of 193 member companies of the CXL consortium, but overall research of this technology is kind of limited, since there's a lack of actual devices available. So unfortunately, the only way that you'd be able to research on this would be through either some very basic x86 or FPGAs, or emulation via QEMU and NUMA, and that has its own limitations. So if you're doing research via ASICs or FPGAs, you are probably limited to a single host setup, since there are no actual CXL switches. So these are going to work as only a memory expansion device for a single system. So you can do some research on like memory tiering with this setup, but not really anything that's either sharing the same data set or multiple systems accessing the same device. Also, if you're doing research on this, you can use emulation. However, this obviously lacks the microarchitecture modeling. There's no accurate data on DRAM access delays. Now, there has been some simulators that have been created for this, but they either lack the full system capabilities or they can't really simulate multiple hosts. So this is where our project comes in. We started this with a few goals, which is modularity, as gem5 is known for. Obviously, we want to have multiple devices to be able to, we want to be able to simulate multiple devices in a system. We also have the goal of implementing this for a heterogeneous ISA cluster. And we want to have the coherent address space so we can address any sort of memory from other systems from the specific system. And overall, all of these features are leading us to the goal of being able to do research in this area that has not been able to be done before. Cool. So let's talk a little bit about modularity. So gem5 is known for modularity. Mainly, say the library gem5 if you're using it. Let's say you have this board and it has these characteristics. So you have a 12-core x86 CPU and you have your message level cache and whatever memory you want to throw in there. And if you want to switch your simulation, you want to add another type of cache, you can simply slot that out and then slot a new cache in. And there you go. That's your gem5, your regular gem5 simulation that you can do right now with mainline gem5. So this is this type of modularity that I'm talking about when I say that our goal to implement the system was to make sure all of this is easily modularized. So here is our current infrastructure, the goal that we have. So let's say you have this cluster that you want to create, and this would be kind of like that server rack. We would add mini boards to that cluster, and we'd be able to swap out whatever board for another board that has different characteristics and simulate that system instead. Now, these boards are regular gem5 boards. The only change we've made to them is we've added this parameter for remote port that connects into the cluster. And of course, we want to make sure that these are easy to use and reproducible. So we've created this standard library object for a CXL subsystem. And this subsystem is going to be what you can add this remote memory device with. So you can configurize what you want to add there, what type of memory. So let's say here you have two different systems with a 16 gigabyte 8-channel memory, and you want to add this 32 gigabyte channel. You can simply slot that into our cluster object via this standard library CXL subsystem object, and you can do that and run that simulation instead. Very easy, simple to use. Just the same sort of script you've been running already for gem5, you just slot that in. Cool. So let's talk a little bit more about this subsystem, a little bit more on the meat of it. So to do this CXL subsystem, we have implemented a new Slick protocol and alongside a few new Ruby memory controller objects. So here's a graph or a figure showing how that kind of works today. So you'd have a host controller object for each of the host boards that you have, and all of these would connect into a CXL network, and this network would then connect to this device controller. Unfortunately, today we are only able to simulate a single CXL device, but that is something we will be working on, as I will cover in the next few slides. And of course, all these boards are able to communicate with this device and address this device to, use it as a memory expansion device or as a method of communication with other boards. So this network in the middle that I had shown in this previous image is fully user customizable, like other networks in gem5. So here's an example of a couple user networks that we've implemented ourselves. So on the left there is the peer-to-peer topology. Now I couldn't make it as big as the tree topology because this is from gem5's output files. So if I made it with the 32 controllers that we have here, it would just be unintelligible. So, and then we've also implemented this as a tree topology here, connecting the two host systems that we have to this device with 32 channels of, I think it was DDR5. And obviously, our goal was to be able to run this in full system. So here's an example of how we did this very simple hello world example of writing to the remote board and reading it back. So you can see here we boot on Linux and we set up this remote board. Now we show this device through Linux as a DevDex device. So it's really, you're able to use this from a workload perspective with mmap like any other device. So our existing prototype and limitations. So in conclusion, I wanted to say that we have been able to create this cycle level CXL simulator that's able to do full system simulation in a cluster of machines that all have access to the single memory expansion CXL device. They're able to communicate via the single expansion CXL device. This cluster is fully modular, both in the number of host systems and characteristics of these systems, and as well in the characteristics of the device. And we are also able to implement distinct network topologies connecting all the hosts in the device together. We do, however, have a few leftover limitations, which is we currently can't run really non-read-only shared memory workloads. I mean, you are able to run those. The only difficulty is since we haven't implemented the memory coherence yet, you might run into some issues since these hosts are going to be caching these, this memory sort of range and making changes to that in the cache, and the other hosts can't see it. Now, one way you could kind of overcome that would be to make this memory range uncacheable. Unfortunately, that would penalize you heavily on performance. So due to that, one of the things that we're working on is implementing the CXL coherence protocol. So we are able to run these shared memory workloads that can work together on a single data set. We also have an existing limitation of long simulation time. Unfortunately, gem5 is already slow, as the previous presentation showed. Now imagine adding multiple systems to that and multiple full system boards that makes it even slower. For that, one thing that's not out of here, but we are working on is parallel simulation. Since these are completely different systems, we are trying to implement them in a way that allows us to run each system parallel to each other and be able to just synchronize at the time that they write to the device that they're using to communicate. And then, of course, the other things that we are currently working on are multi-device simulation. So you're able to add more than just one memory device and maybe have it in a way that one device is only available to certain systems and the other to other, or just make a memory pool like I showed in the first figure, and having a heterogeneous ISA cluster. So being able to run systems like ARM, x86, and RISC-V all in a single cluster. With that, I'm going to conclude. Thank you, and I'd be happy to take any questions.
Questions for Leah?
Hi, thank you for the presentation. I have a question related to the network interconnection that you are going to use. As we are kind of facing two different environments, one I would say more local and another one more related to the CXL memory, more remote. So how many network interconnection are you using, and if you're using just one, how do you handle then the different parameters like bit size or everything like that, more related to different environment between remote and local?
Yeah, so the network that connects sort of all of these devices and whole systems together is completely customizable. So you can add as many switches as you'd like and make them as fast or slow as you want. I don't know if that answers your question.
Okay, yeah.
Yeah.
Okay.
Matt Sinclair, Wisconsin. Yeah, this is super cool and super important. So nice job thus far.
Thank you.
I'm curious, you mentioned these changes to Slick.
Mhm.
Do you have, and I realize they're kind of in progress, so if the answer is I don't know, then that's okay. But do you feel like it's going to plug and play nicely with existing protocols, or is it kind of its own world where once you go into the CXL world, you have to have the new Slick that CXL approved?
No, so these plug in fully with the existing
Make sure you
protocols.
repeat the question.
Oh, sorry. The question was if the Slick protocol that we implemented for CXL plugs and play with nicely with the existing Slick protocols. So yes, these plug in fully with the existing protocols because this is at a different sort of level than existing protocols. So existing Slick protocols are working in the cache. These are going to be after sort of your cache, and these connect to your cache Slick protocols. We have actually tested these with this system with I think it was SMESI 2 level, as kind of shown. Yeah, you don't have to really make any changes to existing Slick protocols. The changes we've made is we just created a new protocol that functions at a different sort of place.
But there has to be an interface then to enable that, right? I mean, that's what Chai and Spandex and CAPI and all these other protocols, they've built interfaces to allow that kind of behavior you're describing to have work. Have
Yeah.
you built a similar interface here?
Yeah, we built a similar interface. We have, so basically we've changed, the current, gem5 models to add sort of this new memory controller-like object, that works as a port for your, remote device. And that is what connects into this new Slick interface. And from then on, it's just a different, protocol that works on its own sort of for world.
Okay, I know you're in the middle of that, but having written, one of those protocols, I feel like the devil is always in the details about how they communicate with one another. So it'll be interesting to see how you get that to work effectively.
Yeah, definitely, I think, the interesting part is gonna have the coherence,
Yeah.
working with it.
Great. Thanks, Daniel.